take this opportunity to introduce Professor Van Venskotten. Professor Van Venskotten completed his PhD in biophysics from University of California, San Francisco. He completed his Bachelor's of Science in Biology prior to that from MIT. His primary areas of interest within artificial intelligence are MLOPs, time series analysis, causal analysis. Currently, he serves as the head of data science and AI for Kraft Heinz, a Fortune 500 consumer packaged goods company. And his particular department functions across the entire corporate space, from deploying IoT in our manufacturing lines, in their manufacturing lines, to deploying shared generative AI tools, to forecasting top-line business growth. Professor Van Venskotten is an adjunct professor at the University of San Diego and teaches in their applied online and off-campus also artificial intelligence program. We are deeply honored to have him teach this unique masterclass on introduction to neural networks and deep learning to our audience today. Thank you, Professor. Very warm welcome, and over to you now.
Thank you very much. Well, it's very nice to meet everyone. Like I try to say at the beginning of all of my academic presentations, if there are any technical difficulties, please let me know. It's impressive how many PhDs can struggle to connect to the internet or do share screens or anything like that. So please reach out in the chat if we're having any issues. Now, as mentioned, I am one of the instructors for the online artificial intelligence master's degree. And when I was asked to come up with a presentation and a topic to present today, I actually thought I would use one of the lectures that you would actually receive as a member and participant in the master's degree program. So what I'm going to walk you through is one of the 4 presentations that I give in our deep learning module so that you can get a taste of what this program is like. And part of the reason why I selected the deep learning track for today is, as we know, generative AI is all the rage. We're all talking about ChatGPT, transformers, and the like, but very few people, I think, understand the foundations of deep learning, not just generative AI, not just generative adversarial networks or all of the applications that exist, but really, how does this tool fundamentally work? So today, we are going to take a journey through deep learning. Now, I've spent the last 15 years or so of my career in the data science and AI field, and what's been perhaps the most fun is seeing how really the last 10 years has been all about deep learning. You might be surprised to know that deep learning was originally proposed back in 1946, and there have been previous attempts to lean into deep learning, even going back to the 80s, that all really seemed to fall by the wayside. But in the recent era of big data and cloud computing, this set a foundation for an explosion in deep learning. So back in 2014, we had computer vision, that is, the ability to recognize images and patterns in pictures, become a neural network problem. And since then, we have seen applications such as AlphaGo, Google's very famous deep learning program that plays the game Go. We've seen transformers come online. We have seen GPT-3. We've seen GitHub Copilot. We've seen ChatGPT. All of these elements that really point to how impactful deep learning is. And one of the most important quotes that I've seen, because I frequently get asked, what is the best machine learning algorithm? It actually comes from a famous French researcher, Francois Chollet. Now, you don't have to read this entire quote, but think of the takeaway as follows. If you could choose only 2 algorithms to understand in your career, you would do gradient boosted trees and deep learning. Now, gradient boosted trees we're not going to talk about today, but this is the approach that dominates structured data. Think of anything that you could put in an Excel file format. That's great. However, deep learning is what you use when things get tough. Think of areas where you don't have structured data, right? Think of things such as images, protein sequences, whatever it might be, that's where deep learning shines. And this statement here, I can actually confirm as a practitioner in the field that deep learning is one of the foundational tools you need to have in your toolkit to be an AI practitioner today. Because as I mentioned, deep learning is pushing the boundaries on so many different fronts. We're all very familiar with ChatGPT, with the ability to have conversations. Think about all of the data that flows in and is part of that conversation. The algorithm needs to understand semantically what you're asking it. It needs to have an entire world of knowledge, and it needs to be able to have a back and forth. That is a great example of, shall we say, unstructured or complex data. For me, as a former biologist and biophysicist, another area that deep learning is really pushing boundaries is in biochemistry. We can now give a deep learning model a sequence, the DNA sequence of a molecule that we've never seen before, and it will predict with surprising accuracy what that molecule looks like in real life. And this is an extremely important application because it enables researchers to design biomedical drugs, perhaps other biostimulants if you want to increase a certain biological process. In my personal opinion, solving this problem using a tool known as AlphaFold, I think is going to win the Nobel Prize in the next 10 years. Just my opinion, but that's where I stand. Then lastly, if we think about Tesla, if we think about self-driving cars and automobiles, just think of how complex that problem is. You need to recognize vehicles versus pedestrians. You need to recognize the lines on your road, right? And think about having to do all of this in real time as you're driving down the road, as perhaps people are stepping out onto the road, as your GPS is telling you you need to navigate somewhere else. This isn't a static problem, it's very real time. So these are just three of many examples of how deep learning really is expanding at the forefront of artificial intelligence and gives you a taste as to how it's going to continue to shape humanity in the years ahead. So how did we get there? Well, when the field of artificial intelligence started, what researchers thought to themselves was, okay, we have a goal. We want to model human intelligence. That's, in essence, the goal of artificial intelligence. Well, if that's our goal, shouldn't we think of building systems that kind of function like the human brain? And this led early AI researchers to think about the neuron. Now, the neuron is the building block of the human brain. So within our brain, we have many neurons that are interconnected to each other. In fact, if you looked at a piece of brain that's just the size of a grain of rice, very tiny, in there you would find well over 10,000 neurons, and they each would form about 6,000 connections. Think about how massive and interconnected that whole network is. Now, those neurons, they're optimized to do a couple things: to receive information from other neurons, to process that information in a unique way, and then send that result to other neurons further down the road. Now, here's a diagram of the human neuron, and we'll point out a couple of things. One is we move from left to right, the dendrites. This is the spot where your neuron is going to receive input or signals from other neurons, right? They're all interconnected. Then there is also the cell body, an axon. Now, you don't have to worry about knowing too much of what these things do, except to say that this is where that information actually gets processed. And let me put my laser pointer on as we walk. Here we go. So essentially, we've taken in our input. That input is modulated. Something happens to it. And then ultimately, that signal is sent in some form to the next neuron. So input, processing, output. The next question is, if we can take this three-step process of receiving inputs, doing something with that signal, and then modulating it, activating on it, can we create a mathematical representation of the neuron? And it turns out you actually can. So all we need to do is we need to have a way to read inputs, do something with it, and then send a signal elsewhere. So let's actually look at the math of what is taking place there. Well, what we're going to do is the mathematical neuron, which is what you're looking at here. This is how it functions. You receive inputs. This could be, say, features that you're passing into your neural network. It could be outputs from other neurons upstream, because remember, this whole system is interconnected. So you have these inputs, and then what do you do? Well, after lots of historical trial and error, the structure that was determined for an artificial neuron is we keep it simple. We are just going to create a linear combination of these inputs as our first step. Okay? So what that means is we will multiply those inputs by some weight, and then we will add them together with a bias term. So we're simply doing a linear transformation. We'll call that Z. What then happens is we've received our inputs and we've amplified our signals. That's 2 out of the 3 steps we need. Then we need to do an activation function. Now, the biological inspiration for the activation function is that neurons are actually very interesting in how they choose to send or not send signals to other neurons downstream. There was essentially a system that was uncovered that says, well, they don't always send down the signal. It has to be above a certain threshold. And that then gave AI researchers the inspiration to add this next term. This term is known as the activation function. For those of you familiar with the sigmoid function, that's exactly what this is. And what happens is we take our linear inputs, all right? We take our linear inputs and we actually plug it into this sigmoid function. That's our activation function. Now, we have not yet talked through how all this math comes together and what it does. I'm simply laying the foundation as to the what. And we'll get to the why in a second. Okay, let's keep going. Now, we have defined an individual neuron, but remember, we need to combine them if we really want to mirror the human brain. So what we do is we take our neurons and we connect them. So each neuron is going to be connected to those before it and those after it. So remember, if we think about the inputs, right? The X1, the X2, and the X3 on the previous slide, this right here can come from these different layers, right? So just keep that in mind. We built the neuron, and now we want to layer them. Okay, so we've talked about the what. Now let's talk about the why. So the way that this works is we need to say, if we build our mathematical representation this way, what does it get us? The reason it's powerful is threefold. The first is this actually creates nonlinear boundaries. Now, for those of you who have some exposure to machine learning prior to this, you know that in machine learning, essentially what you're trying to do is you're trying to draw a complicated line between, say, class green and class red to delineate between the two. That's called the decision boundary. Or you are trying, if you're doing a regression type problem, you're trying to fit a curve to complicated data. Now, if we think of simple problems, right, going back to the idea of having tabular data, right, structured data, the simpler methods like linear regression can help. But if we think of complicated problems such as image recognition, predicting the structure of a protein, you're going to have some pretty darn complicated boundaries that you need to fit. And deep learning is great at this. And in our class, we actually go through the math of how having that activation function makes this magic happen. But we'll talk a little bit more about it in a second. Now, the next reason that deep learning is so powerful is automatic feature engineering. As you get into machine learning, where you spend most of your time is in cleaning and pre-processing the data you put into your algorithm. And one of the most complicated steps is feature engineering. Think of it like this. If we have two inputs, let's call them X1 and X2, how do we want to show that data to our algorithm? Well, we could just directly show the algorithm X1 and X2. Alternatively, well, maybe we should take the square of X1 or X2, or maybe we should multiply them together. And what you see is that if you increase the number of inputs to your algorithm, the number of possible combinations gets pretty big. But here's the nice thing that happens with deep learning. In deep learning, the model does this automatically for you. Essentially, the way it does this is we have so many neurons and we just start them randomly. Remember, think of those weights, that linear transformation. We randomly put values, different values in each of these neurons. What that does is it essentially automatically gives the deep learning model access to all of these possible combinations. And in the process of training the model in supervised learning, the model learns what is important and what isn't. So perhaps it says, well, if there's 3 inputs, this term is important and this term is important, but I can, ignore all of the rest of them. So that's a very powerful model. And this is important because if you think of these complicated problems, again, going back to the idea of what a molecule looks like, it can be very hard for humans to say, well, what are the right features, the right kinds of data that an algorithm needs to know in order to predict its structure, right? So that's why deep learning can be extremely powerful. It automates that process. Now, lastly, if deep learning can, in fact, create its own features, the third powerful component is something known as hierarchical feature learning. As an example here, let's say we want to build an algorithm that identifies famous celebrities like Tom Hanks. What we will do is we'll have a neural network with multiple layers, right? We said that in a neural network, you usually combine neurons together. The outputs of one become the input, so on. Something very interesting happens in this network as it learns these features. It turns out that early on in the network, if you look at what are those neurons kind of at the beginning doing, they're actually learning very basic shapes like lines, edges, circles. And what's really cool is if you then look under the hood and say, okay, what happens next? What does this layer of neurons, what are they doing? Those neurons are actually combining those basic shapes into more complicated features. So in this case, it might take lines and edges and say, well, in a certain combination, it's an eye. In a certain combination, it's a nose. And then if you keep looking on, what the next layer of the neural network does is it takes these features and assembles them into faces. So what you're seeing here is that this network actually learns how to build from basic shapes to body parts to faces, how to go from a picture of a human to identifying a human. Now that's pretty crazy if you think about it, but deep learning does this automatically. Let me give you another example of how this works. Suppose that we are selling a product and we want to predict its demand, right? How much are people interested in this component? Well, let's say we have 4 data points, 4 features or inputs. We have the price of our good. We have the shipping cost of our good. We have, let's say, how much we spend on average for marketing this good, whether it's advertisements, product placements, things of that sort. And then lastly, we have the material, right? In this case, it's the quality of the material, how much we spent on it. Is it plastic or is it metal? Here is how automatic hierarchical feature learning might happen in a neural network. It will take price and shipping cost, and it will learn that, well, I can actually create a synthetic feature called affordability, a function of price, a function of shipping cost. It knows that the combination of those two will, to the customer, be a metric of affordability. Now let's say it takes marketing. Well, marketing spend is great, but the neural network might say, well, this feature I can actually call awareness. And then let's say we take both the marketing and the material we used and the price. The hierarchical feature that the neural network might define is perceived quality, right? So you can see how what neural network is doing here is it's taking these basic building blocks and assembling them into higher order features to ultimately predict demand. Okay, now let's talk about the general neural network architecture. You saw this picture before, but it's important to call out that there are 3 specific layers that we need to talk about. There is the input layer. This is where you load the data. So the next layer, and there's usually more than one of these layers, is known as the hidden layer. So this is where we have all those magic nonlinear transformations, we're learning features, hierarchy, where all the magic happens. Lastly, we have the output. In machine learning, in supervised learning, depending on what you want to do, you need a different output. If you're trying to, say, predict the price of the stock market, that's a regression problem, and you need your model to output a number. But if you're trying to do a classification problem, is this a photo of a dog or a cat? You're actually going to want to return a probability. What is the probability that this image is a dog and the image is a cat? And this is what the output layer does. So input, hidden, and output. Now, here's where things can actually get a little bit complex with neural networks. You have probably heard it said that GPT-4 ultimately has billions of parameters. Well, where does that come from? This is where it comes from. Let's take a very simple neural network. Let's say there are 2 inputs, just 2 features, x1 and x2, 2 data points. What happens if we pass it into a network that has 6 neurons in your input layer, 8 in your hidden layer, and 4 in your output? This is actually a very simple neural network. Well, you'll remember that inside each of these neurons, we're doing a linear transformation, right? So for every input, we have a weight, and then we have a bias term for the whole thing. Each of these neurons is going to have separate weights for x1 and x2. So that means there's a total of 6 times 2, or 12 weights across all of these nodes, and 6 bias terms, right? So each of these linear combinations, right, linear transformations, that is meant to have its own bias term. So this layer has 12 plus 6, or 18 variables or parameters. Now, what happens when we take those outputs and pass it into the next layer? If you do the same math, you end up with 48 weights and 8 bias terms. And then lastly, if you even have just 4 output nodes, you have 32 weights, 4 biases for a total of 36, right? So right now, we're at about 100 parameters with something very simple. It turns out that even small neural networks ultimately can have hundreds of thousands or millions of parameters. So this is ultimately where you end up in a spot of having billions of parameters. So remember, parameter numbers get very big very fast. That's why we run into some of these crazy levels of parameter sizes. Now, we're going to start to get a little bit more technical here. Again, I am walking you through a presentation that you will see in class, so it's okay if you don't understand all of these terms. But it turns out that neural networks are actually trained and built very similarly to more traditional methods like linear regression, or ultimately, let's say logistic regression, let's say tree-based methods. We're going to use methods known as gradient descent, loss functions like mean squared error or binary cross entropy. The main takeaway from this is that neural networks, though they have many more parameters, can be trained very similarly. There is, however, a new term that you encounter when you build a neural network, and it's called an epoch. Now, an epoch is when, in gradient descent, in supervised learning training, you make one complete forward pass and backward pass over all of the training data. Forward pass is when you are fitting your predictions for each data point and calculating the error, right? In regression or classification, we have prediction, we have the actual answer, and then we look at the difference. And the backward pass is where we update the weights, right? Remember, gradient descent is all about updating the weights of your algorithm. But there's an additional layer of complexity when you talk about neural networks. So the complexity here is that in traditional machine learning, and this didn't come out well, when we calculate the derivative of, let's say, no, this is not working. There we go. Our loss function with respect to the weights, this is how you determine and fit a model. You have all of the gradient weights calculated directly on the variables at the same time. But in a neural network, what ends up happening is you have interdependencies. What does it mean to calculate the weights for a hidden layer when there are also weights for an upstream layer, right? Remember, in a neural network, you have many, many layers of weights. So how do you do this when there's this interconnectedness? The trick is that you use a method called backpropagation. And the general principle behind backpropagation is that you start by calculating the error, the difference between your predicted output and the actual output. And then you actually send that error backwards to each layer of neurons in that backward pass we talked about before. So in essence, you say, okay, here's my error term. I'm going to calculate the gradient at this layer, update my weights, and then go back and back and back. So this is where the term backpropagation comes in. So what this means is we actually have a way to fit all those billions of parameters. Now, I'm going to end this lecture by walking through the mathematics of backpropagation. I tell my students this can be a little bit risky because this math is not super intuitive until you stare at it for a little while. But I believe that if you understand backpropagation, you understand the essence of deep learning, and it sets you up for understanding transformers and every single other advanced technology. So let's walk through backpropagation in our remaining time. I'm going to start with a very simple representation of a neuron, slightly different perhaps in visualization than what we did before. So we have our input, right? All those data points or features. We'll call that X. Now what happens is within the network, we have weights applied to X, and we have the bias term. That becomes Z. So think of it as this generalized equation right here, right? You have the weights times X times your bias. Now, we also apply the activation function. We'll call that A1. And so A is simply the sigmoid function, which we talked about earlier, applied to that linear transformation. Now, let's take this notation and let's use it for every single neuron. So we started with the weights for neuron 1, weight L minus 1, and then weight L being the last layer. Now, at the end, we have the actual output, right? Whether it's a cat or whether it's a dog, or the actual price of the house. And then we also have our prediction. That's what that final activation is. What this means is that our error term, if we use the mean squared error, is going to be our prediction, that final output, minus the actual value squared. Okay. Hold that in your heads for a second. Now what we're going to do is we're going to take a slightly different look at what we just laid out. And let's just look at how all of these different variables, the error term, the activation function, that linear combination, how they all engage together. Well, the final error term is a function of y, the actual value, and our predicted value. Again, all that we're saying is that that's this term right here. It's a function of a and y, okay? Now, we can apply similar logic and say a is just a function of z. Remember, because we just apply that sigmoid function to z. Now, z is that linear combination. It takes the previous output of the previous node, that's what this activation of the previous node is, and the weights and the bias. So again, all we're doing is just mapping what variables influence what. So we've got that. Now, to finalize backpropagation, to make it work, we're going to use a bit of math known as the chain rule. What the chain rule says is that if you want to take the derivative of a nested function, so f of gx, well, what it is it's f prime of gx times g prime of x, right? Two derivatives, but the first one includes the nested function. Now, I will leave it as an exercise for the reader to justify the following. So if we want to find out the gradient or the derivative of the cost function with respect to the weights, which again is exactly what we need to fit a model, then this is what you end up with. By the chain rule, this is the gradient of C naught, our cost function with respect to A. The y term drops out because that's a constant, times the derivative or the gradient of A with respect to Z, times the derivative of Z with respect to W. Okay, that's just, if we can find each of these components, then we'll be able to get this math term and we'll be able to fit our algorithm. So let's go back to those equations that we specified on the previous slide, because these are the derivative. We essentially need to take the derivatives of these functions to calculate these terms. And the beauty is that because of how we've defined these terms, it's very easy to do. So this term, the derivative of our cost function with respect to A, well, if you remember your basic calculus, that's just 2 times the activation function of L minus Y, right? This is the variable. And so it's just 2 times this. Basic calculus. Now, what is next the derivative of A with respect to Z? Well, that's just going to be the derivative of the sigmoid function as a function of Z. Now, the sigmoid function is actually very easy to differentiate. I'm not going to write all the math out here. But then lastly, we need this term, the derivative of Z with respect to the weights. And that's just a function of the previous input. Great. What does this mean? It means that if we put all of this together, this gradient, which if we can solve it, lets us fit our deep learning model, is simply a function of the activation value from the previous layer times the derivative of the sigmoid function applied to this linear transformation times 2 times the final activation value minus the final value. Now, here's the thing. When we did that forward pass, when we let all the data flow through, we actually ended up getting each of these values. These are real numbers that we have. And as a result, we can plug them in and we can figure out what the gradient is for this first layer of weights. So what this means is we have solved the first layer backpropagation. Now, I'm going to leave it again as an exercise that if you simply extend this type of model and say, well, okay, now what we need to do is figure out the derivative of layer minus 1, right? Because that's the weights of the neuron layer further back by one more step. You actually end up with the following term. And each of these components is, again, something that we calculated when we did that forward pass, except for this weight term. Remember that in gradient descent, we always update our weights a little bit by some learning rate times the gradient. Well, if we do that, using the math that we just had before, we can calculate this number and plug it in and figure out the weights of the layer before. But you see that in order to get this term, we actually have to take this first step and update that first layer of weights. So this is where backpropagation's iterative approach to calculating the gradient comes into play. Now, again, I don't expect folks to understand this through the first time, but I highly recommend spending the time to think on this if you want to be a deep learning expert, because it is how you will set yourself up for the future. Okay. Now, there's one last term that one last concept that I always want to introduce my students to when we discuss deep learning. Now, again, when we update the weights, it's the weight itself minus the derivative, right? That gradient at that level times some learning rate. But here's the challenge. If we think about epochs, there's a couple of different ways we could use data to train our algorithm. So we could say, all right, for each forward pass, right, when we're doing these calculations, I'm going to throw all of my training examples in. Let's say I have 1,000 of them. Those training examples ultimately will flow through, and then I'll be able to do one level of calculating backwards, right? One forward pass and one backward pass is all I can do because I use the data. Now, what you can also do is something called mini batch gradient descent. The idea here is that you don't train your model on all the data at once, you break it up into chunks. So in this case, instead of all 1,000 data points, we use 200. What ends up happening is that we are going to go forward and backward, forward and backward, forward and backward for all of these mini batches. So that means, whereas in this epoch, we only went forward and backward once, in this epoch, since we broke things up, we went forwards and backwards 5 times. And then lastly, if we do 100 in each of our batch sizes, now we have 10 total batches. And this gives us 10 forward and backward passes. The reason I call this out, and this is what we cover in our subsequent lectures, is that this is actually a parameter you need to think very carefully about when training your algorithms. However, at the end of the day, epoch means one complete forward and backward pass over all the data. So you have to add up all of these batches if you want to understand how many times do you go backwards and forwards to do the calculation. Okay, so that is my presentation. So at this point, I think I will turn things over and look at some of the Q&A. So let's take a look. All right.
Thank you, Dr. Van Scotten. That was very informative, I'm sure, for our audience too. We have a couple of questions which are related to the class, which we'd like you to answer. Would you like me to read those out, or for the benefit of the other attendees as well, maybe they could benefit from the answer? So we have Renuka, who wants to know, does a disease recognize, how can, perhaps maybe she wants to ask, how can we recognize a disease using the OCT technique with deep learning and AI?
All right, let's see. Yep, so in this case, I assume that what we're saying is optical coherence tomography. There's actually a couple different OCTs. So in this case, I'm going to treat this as a, how do we recognize diseases from images? So in this case, you would use it like a standard image classification problem. Let me go back a few slides. Maybe this will help. All right, let me actually scroll back and make this easier on folks. Essentially, what we want to do is a version of this problem right here, right? Where instead of looking at vehicles, we might want to say, well, this is actually a tumor, or this is a certain feature that enables us to classify a disease. So essentially, it's the exact same problem. You use your deep learning model in 2 stages. The first one is you identify the important features. Maybe this is a tumor, or this is a form of internal bleeding. You can have your algorithm stop there. You can have deep learning return a list of all the things that it saw and the physician can diagnose. Or what you can do is you can build another algorithm on top of that one that says, okay, the first stage of the algorithm identified all those items, right? Tumors or bleeding. I'm going to build another algorithm that says, based off of that list of features, what do I think the diagnosis is, right? So a certain tumor size in a certain location might mean one diagnosis, another location might mean another, right? So that's how you can do this. You can actually use it as both input for a physician, you can automate the whole process, or specifically, you can put them together. All right, hope that one helps. What's the next question?
Thank you, Professor. The next question is from Anand. It's asking for DL weight updation. How is learning rater, LR, decided? What is the logic or algorithm for the same?
Yep, great question. It turns out that this isn't something that you can reason your way into. You simply have to try a number of values. So if folks have ever heard of hyperparameter tuning or grid search, the idea is that for parameters like this, and there are many, you simply try a bunch of different combinations and see what works the best. So you might do a learning rate step size of 0.01, 0.001, 0.0001, and so on. And then early in your process of building a deep learning algorithm, you'll see which one performs the best, and that's what you'll use. So it's perhaps not as scientifically elegant, but it's how deep learning and really machine learning in general works. You try things and see what works the best.
Thank you, Professor. The next question is from Yash, who's working on HV and wants to build an ML model for devices and perhaps is seeking your advice on that.
So in this context, what does HV stand for? I can think of a couple. I'll need a bit more clarity on this one.
Yash, if you could share that information with us. Meanwhile, Professor, I think what would be beneficial, and we've gotten some of these questions earlier also, to throw some light on how the knowledge from this masterclass on neural networks and deep learning is particularly helpful for those who are attempting to build a career in the field.
Yep. Well, to answer that question, I'm going to go back to the quote we talked about at the beginning. If you could only pick two subjects to know, if you wanted to be an AI practitioner, you would pick deep learning and gradient boosted trees. What we covered today is the foundation that helps you understand deep learning. There are many practitioners out there who essentially just take the packages that are written in Python or R or the programming language of your choice, and they use them to solve problems, but they don't really understand how it's working, right? So in that instance, you need to know what is happening underneath the hood. What we did today is I gave the attendees here the foundation to know how deep learning works. Now, this is a necessary step, but it's not sufficient. But this is the level of understanding that I, as a hiring manager, as a head of artificial intelligence at a large company, expect my AI engineers and data scientists to have. So this is the foundation that will hopefully set folks up to learn one of the two main classes of algorithms to be an AI practitioner.
Thank you, Professor. Yash has clarified that by sharing HV, he means high voltage.
Yeah, well, so here's what I would say, Yash. Sometimes deep learning is the best approach. Sometimes it isn't. So what I would say as a first step is understand the problem you're trying to solve, right? If you're trying to solve, say, let's say a grid optimization problem, I would actually recommend something along the lines of mathematical optimization, which is a separate technique from this. Now, once you've figured out what your problem is, think about the data. If it's a time series problem, you're going to need to use more time series approaches. If your data is well structured, again, you can put it in an Excel file format. Then what I would say is use gradient boosted trees. Again, that's why I love this quote. It's a cheat sheet, if you will. If your data is extremely complex, if you have many features and you don't know where to start, that's where you can start to use deep learning. But what I would recommend is apply your domain knowledge to figure out what the problem is, the class of problem it is, and then that will show you what algorithm you want to use.
Thank you, Professor. I think there are a couple of questions in trying to ask how this method can be used to detect diseases or some you can share some domains that are used in the healthcare industry.
Yeah. So there's a couple of different applications. We already talked about image recognition. So diagnosing based off of X-rays or off of PET scans or whatever it might be. So that's one big class. Another class is when you use deep learning on text data, right? If you think about all these generative AI tools, you can actually pass in a write-up of symptoms that the patient has. Think of physicians and the notes they take. Deep learning can read in those notes and then ultimately can create a diagnosis. So that's another great example of it. There are other more predictive algorithms. You could use deep learning to also say, what is the likelihood that someone is going to have a disease in the future based on these symptoms? But those are the three elements that I would say. Classifying disease based off of images, classifying disease based off of text write-ups, and then predicting the occurrence of disease in the future.
Thank you, Professor. Someone has a question, Sharon, about using handwritten scripts for evaluating No, using TROSR for
Mm,
evaluating handwritten scripts, and they would like you to throw some light on it.
mhm, mhm. So I might need a little bit more detail on this one. So TROCR, again, if I'm understanding the question correctly, that is a class of algorithms that does this kind of thing. It does image recognition. There are many algorithms that have been trained on handwriting. So the MNIST data set is a very famous one that essentially is a collection of handwritten numbers that are used to train deep learning algorithms to recognize numbers. You can do the same thing by providing examples of handwritten scripts, right? As long as you then also, along with that picture of the script, provide a typed up answer that your algorithm can understand. At that point, then you've essentially created training data for your deep learning model to understand. And again, if we go back to the fact that deep learning creates its own features, that takes the pressure off of us, the humans, because the deep learning will essentially figure out how to recognize a 7 versus a 1 on its own. So those might be a couple of the details I'd say about that.
Thank you. Thank you so much, Professor. I do see that there are some other questions,
Mm,
but due to paucity of time, I know we have to end the class at 8:30. I would request you to share a little bit about your experience of teaching in the program, and why should somebody who's interested in building a career or a specialization in artificial intelligence consider it. Um,
abs
Related question, I think a lot of people still want to know the kind of roadmap that they should follow for excelling in AI and building a career there.
Well, that's easy. The roadmap is completing the master's program through the University of San Diego. So I think it's a good question. Why USD? And what's helpful here is, in addition to being a practitioner of AI at several large companies in several different industries, oh, there's a wasp apparently in here, um, that I also have had the ability to teach at multiple universities. And what sets San Diego apart in my mind is that it is the best combination of theory and practical that I've ever seen. As an example, in 501, the course I teach, you would receive this lecture. At the same time, you would be provided with a hands-on example of, all right, here's how you build a deep learning algorithm. A lot of universities just teach the theory. A lot of, let's say, YouTube videos or boot camps just teach the how to build it. At San Diego, we do both. And again, as a hiring manager, I've hired well over 100 data scientists in my career. You need to understand both sides of the coin to be an effective data scientist or AI practitioner. So I would also say that what sets San Diego apart is that we are also leaning away from what I would call more archaic versions of education. So think of final exams, for instance. And we're focusing more on what will you actually be doing in the real world. And so we focus a lot more on final projects where you're collaborating just like you would at a profession with other students to accomplish something with your deep learning model or whatever your model might be. That is very unique to the University of San Diego, and I think it is one of the best things that students can do in order to show prospective employers that they understand the why behind artificial intelligence, not just the what. So, does that help answer the question for folks?
Yes, it does. And with that, we are at time. I would like to take this opportunity to thank you once again for taking this class and sharing your insights on this very interesting topic. I for sure got to learn a few new things, and I'm sure so did our attendees. I would also like to thank all the attendees for taking time out on a Saturday night to attend this masterclass. As with a series of these masterclasses, we will be sharing a quiz based on the masterclass for you to attempt. And if you score 60% and above, you will be entitled to receive a certificate. It might be unfair of me to not acknowledge my colleagues behind this event, starting with my colleague Alifia, Fanendra, Vijaya, Bhagyalakshmi, and Surabhi. Thank you everyone for putting this together. I would also like to thank all the all the participants who had to give up other things and attend this class. And we hope to see you again for our other events, not just the master classes. Please stay in touch. Please follow us on our socials, and we would be sharing more interesting updates about our programs and our related disciplines with you. With that, thank you everyone, and have a good night. Good morning for you, Professor. Have a great day and a great weekend.
Have a good evening, everyone.